Okay, we are going to look at compound Poisson distributions. So this type of analysis appears quite a lot in actuarial studies, and this is an exam question from a past paper from April 2022. Anyway, let's read it out. The annual aggregate claim amount of an insurer follows a compound Poisson distribution with a parameter 1000. Okay. Individual claims follow a gamma distribution with a shape parameter alpha equals 750, and a rate parameter lambda equals 0.25. Okay, so the relevant exercises are on the next slide. Okay. Generate 20,000 aggregate claim values for this insurer using a random number generator seed of 914. Use the R function head to display the first 7 simulated claim values in your answer. Okay. Determine the mean and standard deviation of the simulated aggregate claim values in part 1. Okay, so those two go together. Plot the empirical density function of the simulated aggregate claim values from part 1, setting an x-axis from 2,600,000 to 3,300,000 and a y-axis range of 0 to 0.0000045. Okay. Question 4. Suggest a suitable distribution, including its parameters, that approximates the simulated aggregate claim value in part 1. And I tell you what, I leave the rest of them there because there's a couple of questions to go through there. There is one that relates to the gamma distribution that comes up shortly, but let's just actually sort of get cracking on this one first. So simulate the problem. So we're dealing with a compound Poisson distribution where the primary process is a Poisson with a rate parameter lambda equals 1000, representing the number of claims. The secondary process, the gamma distribution, gamma with shape alpha equals 750 and a rate parameter equals 0.25. This represents individual claim amounts. So we simulate the number of claims using a Poisson distribution, and for each claim we simulate its amount using a gamma distribution. Okay. The total aggregate amount is the sum of all individual claim amounts. Okay, so that's essentially the game plan here, okay? Understanding the problem. So we're going to run 20,000 iterations of this experiment. So there's a couple of steps to do to set things up. So we're going to set the seed at 914. And then the second part is we're going to create a vector called n. And this contains the number of claims for each iteration. Now this is a Poisson random variable with a parameter 1000, okay? So essentially what we're going to have here is 20,000 values, and each value represents the total number of claims for each iteration, okay? We're going to save this in a vector called S for sums, and again, just initialize it with the 20,000 blank values there, numeric 20,000. So we're going to run through this experiment 20,000 times using a for loop, okay? I is the index. So the first part here is R gamma Ni. So this extracts the total number of claims for that iteration, okay? Which is the parameter for the R gamma variable, just the number of values to simulate. And shape is the gamma distribution parameter, as is rate. Shape equals 750 and rate equals 0.25. Okay, so this will simulate the certain number of claim amounts and save it as x. So the length of x depends on the corresponding value of n. Okay, and we're going to sum them up. So sum of x, and that is assigned to si. So this is the ith value of s. So essentially each successive value of S gets updated with the total claim amount, okay? And when we add them all up there, and then we add them all up, sum them all up, and we save them in S. And then we have the first 7 values, which is the answer to question 1. So we get 2,860,469, 2,915,250, and so on, all the way down to 3,132,371. Okay. There's an alternative approach you can take where you can actually just specify the number of values inside the for loop if you want. That's an approach that somebody else suggested. It's fine as well. It should work as well. Anyway, okay. So the mean and standard deviation, we need to calculate the mean and standard deviation of the simulated aggregate claim. So just get the mean of S, which is 3,283,000, and the standard deviation is 95,263. That one's straightforward enough. That is just working on S there, I should say, not X, S. So what we're going to do now is plot them, and we are given a limitations on the graph that was specified in the question, x-lim and y-lim. Okay, so what we're going to do is plot the density of S, and that's it really. The simulated claim amount, probability density function, and just put in some, how should I put it, just put in some annotation into the plot when you're graphing it. It's very important to do. Okay, so that's what you should get there. Straightforward enough really. Bit of a bell curve on it if you're looking closely at it. So yeah, that's it. And it's centered around 3 million as well. So you were given a bit of guidance in the question about what limits to use for the x and y axis, of course, as well, which helped. Okay. Suggest a suitable distribution, including its parameters, that approximates the simulated aggregate claim value. Given the shape of the gamma distribution, a normal distribution might be a good approximation for the aggregate claim. So we can use the mean and standard deviation from the in exercise 2 as the parameters for the normal distribution. So there they are again, okay? 3,982,000 and a standard deviation of 93,872. So the variance is that value squared, which is 8,812,000, etc., etc. We'll just leave it there. You specify the variance when you're specifying the distribution. Okay, so just you write it out like something like that. If you want to just leave it in as 93,872.61 squared, that is actually probably fine as well, because it makes it almost clearer. Now, this is where I'm picking up. So what we have to do here is simulate 20,000 values from your suggested distribution in part 4 using a random number generator, seed of 914. So essentially what we're going to do here is see if an approximate normal distribution will fit this data as readily as what we have determined empirically. Okay, so our norm 20,000 and mean of S and SD of S, the standard deviation of that S. So essentially this simulates 20,000 values according to the normal distribution, and those are the first 7 values there. Okay, 2,854,076 all the way down to 2,975,351. This looks like it has the same distribution as the simulated data set for where we combine the Poisson and the gamma distribution. So by comparing the two density functions, we can visually assess how well the normal distribution approximates the compound Poisson distribution. So if they're close, the normal approximation can be used for further calculations and risk analysis. So what we're going to do here is we are going to superimpose the theoretical distribution, the normal distribution, on the plot that we have already created. Okay, so the top part there is what we've done already, and lines of density approx distribution color equals red is basically what we have created here. Okay, so it's applying a density plot based on the simulated data to the plot. I also have legend data there, or legend specifications there as well, because that always helps. Okay, and that is what we get. So it does indeed fit the data quite well. So the red plot is the approximate normal distribution. The black line underneath is the simulated claims that we've done previously earlier in the exercise, and they do match up quite closely, I think. So I think that's a success. Okay, we'll leave it there.